optimization. So this first article deals with the main landing gear of an airplane, and it basically looks at two components. It looks at this kind of knuckle component, and it also looks at we have a remote site that the mic is open on. Could you please make sure the mic is muted? There's actually two components. The one that I've highlighted here is just this part where they go from an initial design kind of shape to an optimized topology. The second article, which I think you'll find interesting, a little more mathematical, so there is some heavy reading involved in trying to understand this. But as you get about 2/3 of the way into the article, it gives an example of a chassis that has been laid out as a design space with boundary conditions, with different load cases on it, and it goes through the process of doing topology optimization on a chassis, which you ought to look at and think, well, maybe this is something that would apply to the models you're working on. So here's the design space on the left, and then as it goes through various topology steps, optimization steps, it actually gets into a shape that is optimal. Can you send an email out to everybody online and ask them to mute their mics? Maybe they're not hearing us or something. The third article, which is the homogenization method, the technique that they employ in this paper is where you develop a unit cell. So this is a 2D kind of example, it could be 3D. But you develop a cell that's 1 by 1, and you introduce a void that has dimensions A and B in it. By grouping those cells together, and by varying the void, you can basically eat away at the shape, trying to find the optimal load path that will support the geometry. And so here on the right are just a bunch of examples of parts that have kind of been eaten away using a topology optimization approach where you have a unit cell. Somebody's trying to dial into her. Wonder if I can just turn the volume down on the speakers. So this article does get into some pretty intense math. So that's just an example of the mathematical discussion. You'll find out that it's nothing that difficult. It ends up being a lot of summations. So you're taking a unit cell, and you're basically summing up all unit cells and grouping them together to figure out how much mass you actually have left versus the voids that have been introduced. The fourth article introduces a slightly different approach where it basically defines a unit void. It applies that unit void, so in this case it's using circles as the void, and it's placing a circle at every discrete point that has low or no stress. So if you have a point in your finite element mesh that has 0 stress, do you need that object, that area. You don't, and so it imposes this shape and does a subtraction and just removes that shape, that object, that area out of the object so that it can then reanalyze all of the other points that are remaining in the shape. And so these 4 methods or 4 papers are ones that I would like you to read. The first one is a very fast read, or should be a fast read. The next 3 papers are somewhat more involved. So hopefully by now you've all been introduced 2 or 3 times to different design processes. Okay? So this is one that comes straight out of machine design textbook, if I remember right. The one that we want to kind of look at is more of a linear kind of layout, where we typically talk in terms of conceptual design, we talk in terms of preliminary design phase, we talk in terms of a detailed design phase. The detailed design phase goes all the way through the first build and the first tests, the first physical tests. These design areas somewhat overlap with each other, and the reason that topology optimization has become such an important and such a popular topic is because if done in the conceptual and preliminary design phase, it can have huge cost savings effects to the overall product that you're working on. So let's talk for just a minute about terminology that you're going to trip across as you go into these articles. The first term that we need to kind of look at is referred to as the design space. Okay. The design space is kind of the bounding box. It doesn't have to be a box shape, but it's the bounding envelope that your design fits within. Okay. The design variables, there are a bunch of parameters that can be varied by the optimization process. The response is basically the function that you want to drive towards. Okay? It's you're going to look at mass or stress or displacement. That's the response that you want to focus on. And so you can take this up to where you define objective functions. So the objective functions will be, I'm going to minimize the mass. I'm going to minimize the stress. I'm going to minimize displacement. Okay? And the other thing that you have to do is you have to look at constraint functions. Okay? What are kind of the boundary conditions? What are the things that are going to keep this a feasible design? So what do we mean by feasible design? Well, it's some design that satisfies the constraints that are put on your initial shape. An infeasible design is just one that violates at one or more of the actual constraints. And we'll talk in terms of kind of an optimal design. An optimal design is one that is either the minimum, if you're driving towards that, or the maximum within its constraint settings. So why do we do optimization? Well, across this bottom axis, we have our design process. We have conceptual design, we have preliminary design, detailed design. We know that as we start with the design, we know that there's lots of openness, okay? Lots of things that we can consider and work with, but at the same time, very little is understood about the behavior and kind of the knowledge of this new product. So this orange curve is low, the yellow curve is high. At some point in time, over time, we learn quite a bit about what we're designing and how it behaves and what the parameters